Alright, so when we're trying to look at finding an eigenvalue and eigenspaces, what we're doing is we're taking and solving for the equation when the matrix times the vector equals some number lambda times the vector. And if we have this sort of relationship, what's nice then is that if we wanted to go ahead and raise our matrix to some power and multiply by the vector, that's the same thing as raising that scalar lambda to some power and multiplying it by the vector. So this would be something that's really nice to do, right? Instead of us having to raise a matrix to some power, all we have to do is raise some scalar to some power, which is going to be much more efficient for us to do. So if we could find a way to then no matter what vector I have, if I take the matrix raised to some k power times some u, and u is going to be some random vector, if this forms a basis for the space u is in, then we can take and rewrite u as a linear combination of these vectors. So that would be m to the k power times, if the linear combination's coefficients are the alpha sub i's, alpha 1 v1 plus alpha 2 v2 plus alpha 3 v3, all the way summed up to alpha n v n. And so what we're saying is that this alpha 1 v1 summed up to alpha n vn, this is going to be, I'm going to set parenthesis, is going to be our linear combination representing this vector u. And so if u is equal to this linear combination, then what we're allowed to do is we're allowed to multiply this matrix to the kth power through and kind of go past the scalars. So we can move the scalar over, so alpha 1 m to the k times v1 plus alpha 2 m to the k times v2 plus alpha 3 m to the kth power times v3, again summed up to alpha n m to the kth power times v sub n. But if these are all eigenvectors associated to some particular eigenvalues, lambda 1, lambda 2, and so forth, then this is just the same as alpha 1 times lambda to the lambda 1 to the kth power times v1 plus alpha 2 times lambda 2 to the kth power times v2 plus alpha 3 times lambda 2 sub 3 to the kth power times v3, all the way summed up to alpha n times lambda sub n to the kth power times v sub n. So what we can do is we could then take any vector, if we have a basis of eigenvectors, rewrite it in terms of what those eigenvectors are, and then use that to use our eigenvalues to find a way to multiply by this matrix in a much more efficient manner. So that way, if we had to do this, if we had to only do this once or twice, it wouldn't be so bad. We wouldn't go through all this process. But this is useful for things we want to do 100, 1,000, 1,000,000 times, which will make it much faster to just multiply some scalars, or raise some scalars to those powers, as opposed to raising one matrix to that power. So our goal then will be able to find a basis of eigenvectors, and of course, if it's a basis of eigenvectors, we're going to call it an eigenbasis. So let's give a formal definition. Given an n by n matrix M, if M has n linearly independent eigenvectors, v1 through vn, then the basis, the set B, which is going to be the set v1 through vn, is called an eigenbasis of M for Rn. So note that you need to have n of them, so whatever the dimension is of the matrix, number of rows or number of columns, since they have to match. This is for square matrices. If you have n of them and they are linearly independent, then you have an eigenbasis created by those. So let's recall the following lemma. So if the dimension of V is n, any set of n linearly independent vectors of V is a basis for V. So if the dimension of V is n, then a set of n linearly independent vectors will be a minimum spanning set for V, and thus a basis. So our goal is then to construct the eigenbasis for M by finding a large enough set of linearly independent eigenvectors. So we want to make sure that the number of eigenvectors we get is equal to the dimension of M. So we want to determine if this matrix has an eigenbasis for R3. So we want to find, in this case, 3 linearly independent eigenvectors for M. So first we'll find the eigenvalues, eigenvectors, and then we can worry about linear dependence. So eigenvalues and eigenvectors. So the first thing we should do is find our eigenvalues. So if we're looking at this matrix, because it is an upper triangular matrix, its eigenvalues will be along the diagonal. So that was something we had in an earlier video. So the eigenvalues here are going to be 2 and 3. But notice that 3 is repeated. So we have 3 twice. So if we wanted to go ahead and solve the matrix equation and try to find the space associated with the eigenvalue of 2, then what we do is take our matrix minus 2 times the identity, which gives us this matrix, and we're setting it equal to 0. So we're finding that null space, and in finding that null space, doing some row operations, we get that, notice that x does not have a leading term, so it's a free variable. So x equals x, y equals 0, and z equals 0. So then the eigenspace associated with the eigenvalue for 2 is the null space of m minus 2 times the identity, which is going to be the set of all x 0, 0, such that x is an element of the real numbers, which is going to be the span of 1, 0, 0. All right, so we've got our first eigenvector, and now we'll want to go ahead and find our eigenvectors associated with 3. Now note that 3 is an eigenvalue that's repeated, so we might have the potential for more than one eigenvector. We're not guaranteed it though. In fact, we might only get a single eigenvector. So let's go ahead on the next page and take a look at that. So now if we look at 3 as our eigenvalue, we're solving the matrix equation of m minus 3 times the identity equals 0. So this is what we get when we take that. And then we want to get some row reduction going on. And we end up with a free variable for y. So this tells us then that x equals 0, y equals y, and z equals 0. So looking at the eigenspace associated with the eigenvalue of 3, it's the null space of the matrix minus 3 times the identity, which is the set of all 0, y, 0, such that y is an element of the real numbers, which is just the span of 0, 1, 0. So here we had one eigenvalue before, we've got another eigenvalue here. So in order to try to find our eigenbasis, what we're going to do is we're going to take and join those two bases together. So we get 1, 0, 0 and 0, 1, 0. So note that this has two vectors. So we will not be able to find an eigenbasis using for this matrix. For our 3, we only have 2 building blocks. But we need 3. So all we're doing is we're just taking a union of each of the bases for each eigenspace and giving us a linearly independent set. So here's a theorem as to why that is. Let M be a matrix and V be an eigenvector with eigenvalue lambda. Then for any scalar C, C times V is an eigenvector for the eigenvalue, or with the eigenvalue lambda. And so the idea here is that it would have to be associated with a particular eigenvalue, and that if it could be associated with a different eigenvalue, if an eigenvector could be associated with a different eigenvalue, we would have issues. And so when we union these sets together, they're going to naturally be linearly independent. All right, here's another theorem. Let M be a matrix and let V1 and V2 be eigenvectors with eigenvalues lambda 1 and lambda 2 respectively. If lambda 1 is not equal to lambda 2, then the set of the vectors is linearly independent. So that's something that is nice for us to work with, and we've got a little bit of a proof for the rest. So let's go back to one of our previous videos, notes, which I can find. A particular example. All right, we'll look at this example. So back in the notes where we first talked about finding eigenspaces for this matrix, we found 2 eigenvalues with 2 eigenvectors. And so if we wanted to go ahead and create an eigenbasis, for this matrix 5, -3, 6, -4, that eigenbasis would be the set 1, 1, 1, 2. So we have one of our eigenvalues or eigenvectors associated with one eigenvalue, the other eigenvectors associated with the other eigenvalue. So what does this mean? Well, it means that if we wanted to go ahead and say find out you could calculate 5, -3, 6, -4 raised to the, we'll say, 5th power times the vector 3, 5. If we wanted to do this calculation, all we would need to do is first take 3, 5 and write it as a linear combination of these 2 eigenvalue vectors. So first we want to see how we can take 3, 5 and set it equal to alpha 1 times 1, 1 plus alpha 2 times 1, 2. And so what we do, we would set up a system of equations. So we get 1, 1, 3, 1, 2, 5. And we would go ahead and we'd take row 2 equals row 2 minus row 1. So we get 1, 1, 3, and we get 0, 1, 2. And then we would go ahead and take row 1 and set it equal to row 1 minus row 2. And we would wonder where we messed up. Oh, no, we're good. We get 1, 0, 1, 0, 1, 2. So that means that if we wanted to find 3, 5, that will be equal to 1 times 1, 1 plus 2 times 1, 2. And so with this in mind, and knowing what our eigenvalues are associated with this, we can take this equation, which will now be equal to, bring it down here, 5, negative 3, 6, negative 4 to the 5th power times 1 times the vector 1, 1 plus 2 times the vector 1, 2. So all we've done is we've replaced 3, 5 with its linear combination from the eigenbasis. That's over here. And so this is the same as 1 times 5, negative 3, 6, negative 4 to the 5th power times 1, 1 plus 2 times 5, negative 3, 6, negative 4 to the 5th power times 1, 2. But what we said is that this matrix times 1 is going to be the same as 2 times this vector. So this matrix times this vector is the same as 2 times this vector, so we get 1 times 2 to the 5th times 1, 1 plus 2 times, since this is the eigenvector associated with negative 1, we get negative 1 to the 5th times 1, 2. And so this is much easier of a problem to solve. We get 2 to the 5th, which is 32 times 1, 1 minus 2 times 1, 2. So we get 32 minus 2 and 32 minus 4. So we get a final answer of 30, 28. So this is the nice thing we can do if we have a set of eigenvalues and an eigenbasis, is we can go ahead and start with some sort of matrix raised to some power times a vector, and we can go ahead and take this and break it down into something that is much easier to raise to the 5th power than, say, the matrix. Now there's a lot of extra work that goes along doing this, and so if we wanted to go ahead and have a reason to do this, we'd want it to be some sort of system or matrix that we were going to use a lot, or something where we knew we were going to be multiplying by very high exponents for that matrix. So in next week's videos, what we're going to talk about is some scenarios where we're going to want to use these eigenvalues and eigenvectors to make some matrices a little bit easier to deal with, and talk about some specific applications where we'd want to go ahead and raise our matrix to a very high power and kind of multiply by it over and over again.